Hello guys, Dr. K here again. So today I'm going to talk about friction, everything about friction that you'll need for college physics, okay? So let's look at this object. You can see this object is on a rough surface. So there's weight acting vertically downward, and because there's a contact, there's a normal force acting in the opposite direction, in the upward direction. Okay, now there's no force acting on it like in the horizontal direction. So that means there's no tendency for relative motion, there's no motion of the object. So there's no relative motion between the surface and the object. As a result, even though the surface can generate a friction force, because there's no relative motion between the two surfaces, the friction force is zero. The friction force is zero. So here I have a graph. For the y-axis, I have friction force, and for the x-axis, I have the applied force. Okay, so that's the graph. I'm going to plot this graph in this video. So at the beginning, since there's no applied force, there's no friction force. So this corresponds to 0, 0, that point. Okay, now I'm going to apply an applied force. You can see that's my applied force, F applied. I'm going to start from a very small value of the applied force, and then I'm going to gradually increase the applied force. Then what's going to happen is there's a tendency to move the object on the surface. As a result, there's going to be a friction force opposing the motion of the object. The object is trying to move to the right. As a result, the friction force is towards the left. Okay. However, the friction force is static because the object is not moving. There's no relative motion. So you're going to gradually increase this applied force. So then the graph is going to look like this. So this is the applied force. You are going to increase the applied force gradually. As a result, the static friction is going to increase gradually. And then the data will fall along a line like this. Okay, so this part is what we call the self-adjusting region for the friction force. That means the friction force adjusts itself for relative to the applied force. If you have an applied force, let's say 5 newtons, then the static friction will be 5 newtons and the system is not moving. This increases to 6 newtons, then the static friction force will adjust itself to 6 newtons. So usually we call this region the self-adjusting region. Self-adjusting region. Okay, so along that region we'll have the applied force, F applied, is going to be equal to the static friction force. So F, lowercase f, usually stand for friction force, and subscript s stands for the static friction force. So the static friction force is equal to the applied force. Okay, and then you are going to increase the applied force at a certain value of the applied force. Let's call that F applied prime. Then you will have the maximum value of the friction force. You will have the maximum value of the static friction force. Maximum value of the static friction force. That means at that F applied value, now I'm going to change this to that applied value, F applied prime value, you will have a maximum value for the static friction. If you increase the applied force beyond this, then the object will start to move. And then what you'll see here is that it's going to slightly drop. The friction force is going to slightly drop, and then irrespective of the increasing applied force, that friction force will pretty much remain the same. And that friction force is what we call the dynamic friction force, or sometimes it's called the kinetic friction force, F of k. Okay, so this corresponds to F of k. F of k. So this is called the dynamic region. That's the dynamic region. This is the self-adjusting region. That's the dynamic region. And then this point, this critical point where you have the maximum value of the static friction force, that's the critical point, okay? If you slightly increase the applied force beyond that, then the static friction becomes the kinetic friction, or the object will start to move relative to the surface. So we have this as a special point where we will have the maximum value of the static friction force divided by the normal force. Okay, so as I told you here, there's a normal force, right? There's going to be a normal force F of n, and then you'll have the weight acting vertically down mg. Okay, so this ratio, the maximum value of the static friction force to the normal force, that's a constant for that surface, that interface. And this is what we call the coefficient of static friction, coefficient of static friction. And similarly, for the dynamic region, we can have another ratio, the kinetic friction, okay, the kinetic friction over the normal force. This ratio is also a constant. That's called coefficient of kinetic friction. Coefficient of kinetic friction. So pretty much this is what we have for friction. We have a self-adjusting region where the static friction force is equal to the applied force and the object is not moving. Then we have a critical point where you have the maximum value of the static friction force. So that means the object is about to move, but it's not moving. So that maximum value of the static friction force divided by the normal force, this ratio is what we call the coefficient of static friction. It's just a number, usually between 0 and 1. It's a unitless number. And that's the second case. The third case is when the object starts to move. That's what we call the dynamic range, where irrespective of the applied force, the friction force does not change. It's the kinetic friction force. It's the kinetic friction force. And similar to this equation, we have an equation for the kinetic friction force over the normal force equals the coefficient of kinetic friction. Okay, so we have pretty much three equations. This is the self-adjusting part, the equation for the self-adjusting. Then that's the maximum value of the static friction force. And then finally, we have the kinetic friction force equation for that. Okay, so that's friction force for college physics in 10 minutes. In 10 minutes, guys.